All right, everybody, let's go ahead and get started. Hi, how you doing? Hi, everybody. Hi, everybody. Thank you. Let's talk about pre-registration. And is it about pre-registration time right now? Open. Okay. If you've been enjoying this class and and you want to take more computer science, let me tell you what the next courses you should be looking at taking. These courses are offered over the summer. They're offered next semester. You should take COSC 052 Computer Science 2, and you should take COSC 030 Math Methods. Okay? Those are the next steps. No matter what you're doing, if you're majoring, minoring, doing the BA instead of the BS minor, this is the next step in computer science. All right. Now the question is, why would you do this to yourself? Right? Why, after suffering through this semester, would you actually do this to yourself? And the answer is that sometimes this is fun. Come on, right now you just finished a project. How many of y'all, when your project was done, you were like, fuck yeah, it's done. It compiled, it worked. You're like, yay, right? Isn't that a good feeling? You get more of that as you go on. And your programs get more and more powerful, and it actually is fun. And the reason I became a computer scientist, actually, I was an electrical engineering undergraduate, and I did not like it. And by the time I realized how much I did not like it, it was too late for me not to be an EE. So when I graduated, I had to take some programming classes, and I found myself after college just like programming things for fun. I was like, it would be fun to I had this puzzle, and I was like, I bet I can write a program, and I would solve it, and it was cool. So it's fun. So as time goes on in computer science, things get better, right? Right now you have a lot of headaches. You get dumb compiler errors that it's hard to figure out. Some of the logic, like between classes and stuff, is just mind-blowing. You don't know everything yet, but as it goes on, it gets better. It's kind of like learning a language, right? Say, anybody here taking Spanish? It's the only foreign language I really know. So when you're first beginning Spanish, you're like, yo soy, tú eres, blah, 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 and that's incredibly dull. And eventually you get up to things like, oh, vamos a la playa, and you're like, oh, that's sweet. And then at some point you actually go to a Spanish-speaking country and you're like, wow, I can talk to people, I can get around, I can swear at the taxi driver when they try to rip me off, right? You get all these experiences because you sat through that stuff that was a grind at first, okay? So this does get better. You're at the point now where you're essentially like, I'm teaching, my son is learning to read, he's in kindergarten, and you're at the point where you're like, see, spot, run. Simple stuff. All right, and it gets better and better as you go along. It also gets worse. I'm not going to lie to you. It gets worse in the sense that if you study computer science and you take more classes, there's going to come a day, probably around your junior year, where you're going to have some incredibly insane project due, and you're going to be like, oh my God, how am I ever going to do this? And your friends who are English and art history majors are going to come along and they'd be like, hey, we're going down to Rhino, is that still open? And you're going to be like, I figured they would have burned that place just to disinfected at some point, and you're like, I'm going to go down to Rhino, and you'll be like, I can't go, and you're like, dude, why are you doing this? I've got like a 3.9 average, and you'll be like, I have a 3.5, and I rock because computer science GPAs are lower, and it's going to be miserable for you because all these other people are going to be working less and getting higher grades, okay? And that part's going to suck. But you know what's really going to be good? You're going to get a job. When time comes to graduate, you're going to get a job. And it doesn't mean that you're going to go off and like live in cubicle land and do programming all the time, but you're going to have skills that are saleable. And computer science students go off to a lot of different places. Some go to grad school, which I think is cool because it's worked out really well for me. Some people go off to finance. Those people end up making a lot of money. Maybe I should have done that. Some people go off to like consulting industries like Deloitte and Ernst & Young and things like that, and they get exposed to a lot of things. They get paid really well. And people go everywhere. People go off to, we have some people go to med school, we have some people go to law school and end up doing patent law and things like that. So there are a wide variety of things that you can do, all right? A wide variety. Okay, so next semester, if you want to take more computer science, take Computer Science 2 and take Math Methods, okay? It's worked well for me, I recommend it. Yes, sir? Okay, so typically what happens is Computer Science 1 is offered in the fall. Well, let me rephrase that. Here's how majors normally do it. If you come in knowing you're going to major, you take Computer Science 1 in the fall, Computer Science 2 and Math Methods in spring, and then you take Data Structures in the fall. Data Structures, when you get there, is the course that unlocks all the electives, pretty much. Data structures, like once you get through there, once you get through data structures, you kind of can do stuff at that point. I mean, you can do stuff now. I've been trying to show you can do stuff. But when you get through data structures, you can do stuff. Okay, bigger, more complicated stuff, and do it pretty well. So data structures is kind of the elective that gets through things. Now, for some reason, math methods is being offered next fall. It normally is not. It's normally only offered in the spring. I don't know if that means data structures will be offered next fall. It might be. I'm sorry, next spring, I should have said. I don't know if data structures will be offered in the spring as well. I'm not sure what's going on with the scheduling. The thing is that we're seeing a large number of students coming in and with interest in computer science. Like, you know, there's another section of this class, right? So like 4 years ago when I taught this class, we had one section of 30 students. And you're already bigger than that, and we have another section, and you know, we were turning people away at the beginning of the semester. So I think what's going on is they're starting to offer some of the other classes at different times as well. Sir? Mm-hmm. What do you want to do with your life is my answer. If you only take one course and you just want to take some more I would take math methods next fall. If you only have room for one of those, I would probably suggest math methods. Yes? It's a prerequisite for math methods. Now, does that mean that you can sweet talk the professor and get them to let you in? Sometimes. But it is officially a prerequisite. Math methods is officially a prerequisite for data structures. Now, sometimes you can talk a professor to letting you in without the prerequisite. You just got to go make a compelling case. So they may or may not say yes. Just depends. All right, let me say one other thing. If you go on in computer science, and this is like long term, and you either minor or you take the BA, like the other degree, you're going to have fewer electives than you will if you take like the full BS, right? That's just natural because you're doing other things. Let me suggest to you 2 electives, and only 2, that you should try and take out of this. And this is not anybody's view but my own. I'm not getting any kickback for directing you into classes, like the professors aren't paying me because they don't get paid anymore when they have extra students. This is just what I believe would serve you best if you only have limited electives. First, take the algorithms course. Now I'm going to warn you something. Algorithms will kick your ass. It is not an easy course, but when you are done with it, you are going to be super sharp. This will help any programming you do immensely. Absolutely. And I don't want to, steer everybody into a programming route, but if you ever go for an interview, regardless of what type of job that's code-related at a place like Google, Facebook, Amazon, anybody else, Twitter, the big cool places like that, all the questions that they ask you on the incoming interview are algorithms questions. All of them. And I know students who are good programmers who have applied to jobs at those places and didn't get jobs because they couldn't do the algorithms part. All right? So the questions they ask you are algorithms, but what is program? What have I told you? What's a program? It's an expression of an algorithm. And this class really teaches you to understand algorithms and really come up with good algorithms for solving a problem. So this class is essentially, you're given a problem, let's figure out an algorithm how to solve it, and let's figure out how good that algorithm is, if we can do any better. So it's kind of the thinking about algorithms part. The other courses you should take if you have the opportunity is a database course. And the reason for this is that databases are incredibly practical. And most work that you would ever do on a computer, if you have any large-scale data, you're going to be using a database. So it's worth taking this class just for the practical skill. So those are my recommendations to you. You can take them or leave them. If you're interested in other things, take that. But that's what, given limited number of electives, if I were in your position, I would take. Okay. Free advice. Sir? So advanced programming is a fine course too. Advanced programming teaches you some programming things that we don't cover in here. It switches to Java, so you would have Java experience when you're done. Some of the stuff that you learn in advanced programming is how to interact with databases, how to come up with like phone applications in Java. So if you want to write something in Android, things like that. It'll teach you some networking stuff. It's useful, but it's nothing in there that I don't believe that you could pick up on your own. Does that make sense? Like, of the electives that are in our system, if you just wanted to sit down and learn Java, you could do that. But it's hard to just sit down and learn algorithms. And you could probably sit down and learn databases. I've never had a course. I kind of taught myself, but my knowledge is patchy because I taught myself. It would be useful to have a course in that, just because everybody uses databases for large-scale data storage. So nothing against advanced programming. I just think that it's, if you have a limited number of choices, that it's not as useful as the others. Yes? What about math electives? There are some. I don't know. I don't have an answer for that. So, I mean, I know that there's different math stuff you have to take, like linear algebra and I don't know, addition, stuff like that. For math stuff, I would recommend a statistics course. I think it might be required now. It is in computer science, but you really should take a statistics course. So, other questions? So, computer science has worked out well for me. It could work well for you. That's all I have to say. So, last time we covered a few things. Any questions, by the way? I'm happy to answer more questions. No? All right, last time we covered a few things. We talked about stuff in classes. In particular, we talked about overloading. We talked about overloading functions and operators. Then we talked about friend functions. What is a friend function? Yes? Yes, a friend function is declared within a class. It says that using this function, another class can manipulate the private parts. Okay, in that class. And then we talked about templates. Templates, I'm not sure I did justice. They're pretty cool. Everything we've been talking about before, data has been a variable. In templates, it's a way of having a function in which the type is also a variable, right? And you declare the type, and it works on any type as long as the function is the same. This time, we're going to cover something special. This time in class, we're getting to the magic. The magic. All semester long, I've been telling you things are magic. All semester long, I've been telling you don't worry about that. Now, we are actually going to get into how some of the magic works. And I'm actually very excited for you for this. All right? Because this is where, in my opinion, things get pretty cool. So, in order to teach you the magic, we need to review how RAM works. What is RAM? Anybody remember RAM? Random access memory. What happens to your RAM in your computer when the electricity goes away? It forgets stuff. Okay, so let's look at RAM. Do you all remember this from the beginning of the semester? Right, we have RAM. It's a bunch of boxes. It goes in a row. I've put a little break there to indicate that it goes on a pretty long time. So we have all these boxes. And I don't remember if I talked to you about this or not. But each box in there is numbered, and it goes from 0 up to however many of these boxes you have. It's probably on the order of 4 or 8 billion. You have billions of these little boxes, and each one can hold some data, some variable, or some object. Now, I'll just tell you briefly, you don't really need to know this. Like one box can typically hold an integer. When we have an object like a refugee that has a whole bunch of stuff in it, what ends up happening is that gets a whole bunch of boxes clumped together in one object. So it takes up more space, okay? Doesn't really matter, but we just kind of need to know that. Now, RAM is numbered. Each box is numbered. It starts at 0, goes up to the top. Because we are computer scientists, we don't use integers for this. Instead, we use, what's that? Hexadecimal. So when we are looking at these addresses, and we will look at some, we will see that they are actually in hexadecimal. And they go from 0 up to, and I only put 2 F's there, but there should be like 9. There should be like FFFF, right? Because the number 8 billion is pretty large even when it's in hexadecimal. So that's what RAM looks like. Everybody comfortable with this idea? We got a bunch of boxes. They have numbers. They're actually in integers, but when we represent the number, we represent them in hex. Okay? Everybody good with that? Say yes. All right. So let's take a look at what happens. Let's say we take a variable, something like int x equals 19, and we run that step in a program. What have we been talking about this doing all semester? What does int x equal 19 do? Sir? Uh-huh. Okay, so it finds one of these boxes, it labels it X, and it puts 19 inside, just like that. Okay? Now, one thing I forgot is it also keeps track that it's an integer, so it should be int x 19. And look, which box happened to get selected that time to put that in? Box number 3, okay? Every variable we use gets put in one of these boxes. The boxes are all numbered, and each box has an address as well as a value. So far, for every time we've talked about a variable, we've talked about its type, its name, or its identifier is another fancy way of saying name, and its value, int x equals 19. But what does each box also have that we have not been talking about? An address. What does each box also have that we have not been talking about? So a variable has a what? Type, and type, name, value, and address. The address has been transparent to us all along. The compiler has been doing everything with the addresses for us. Okay? So let's go take a look at this in a program. So what we're going to do is I've written this program. You can see it's very complicated. What does this program do? Declares a variable named x, sets it equal to 19. All right. Let's compile this and see if it works. Anybody suspect this isn't going to work? Great, and let's run it and see what happens. It worked just as we expected, didn't it? How do you know? Well, it did something, but it didn't output anything. So let's take a look and figure out what's going on here. So if we want, we can see out what x is. Oops, it would help if I put a quote there. All right, how's that? We'll compile it now. We run it, and we see that x is 19. So that seems to be working the way we want, right? Well, let's say we also want to figure out where x is stored, right? Because we know that x is being put in a box somewhere, and we know that box has an address. Let's say that we want to see what that address is. Anybody know how to see what the address is? Anyone? Well, there is a way to get the address of x. And it is an operator. And it's an operator that you've seen before. The ampersand operator. The ampersand operator is called the address operator. Okay? So when we say ampersand x, we mean tell us what the address of x is. So now what we're going to see, when we run this, we'll see x is 19, and we're going to see x is at. And the x at thing is going to be some hexadecimal number. Anybody want to guess what the hexadecimal number starts with? H. Hex doesn't go to H. That's like Spinal Tap hex notation, right? Normally goes to 15. This one goes to like 19. Okay, I'm guessing it's going to be somewhere around what? 7. I'm guessing it's going to be 7e, 0x7e something. 7f. Okay, I was pretty close. So here's what we see. We see x is 19, and we see x is at. And this number right there, 0x7ffb 5b13d8f8, is the box number where x is actually stored. Is that kind of cool? All right. So now we have some insight into what's going on in memory, right? Now we can see where things are stored. Yes? Let's run it a few more times and see where it comes off. So you can see it's moving around a little bit, right? Each time it's 0x7fff, but it's b5b13, 8d, 54. So it moves around a little bit. It's not always the same. What happens is when you run it, the computer goes, essentially what happens is there's a request and the operating system goes, oh, you need some memory? Here's some memory. And so it gives you an address. But it's not always exactly the same. I was able to guess that it was going to be 7ff because I have been doing this a long time. and because I kind of know where things get put in memory, and this type of variable gets stored there. Later, we're going to see it gets stored someplace else, but we don't care, right? For this class right now, we don't care where it's being stored. If you keep going in computer science, eventually someday you'll care. But right now, all that matters is it has an address. All right, everybody good so far? Yes, question? Yeah? Okay, any other questions? Questions? All right, so Mr. Harrington brought up an excellent point. And the point is that we've seen this ampersand elsewhere before. Where have we seen this? Pardon? Yes, as the magic pipe. It is a reference parameter. When we're using a reference parameter, we put the ampersand operator in there. The ampersand in this case is saying use the address, right? So before, what was happening is when we had just a regular reference variable. Wait, no, what's the other one? Reference and value? Value parameter? Sorry, I must have killed that brain cell that remembers that last night. But yeah, value, right? Value parameters, reference parameters, and value parameters. Help me out here. Don't just stare at me blankly. You're staring at me. You're staring at me. Value parameters? Okay, so value parameters, the value gets copied over. Reference parameters, what's happening is we're saying, hey, you're going to be working on a particular thing, but instead of working on a copy, just work at the one that's at this address. That's at this address. And so what's happening is the address is what's being passed as a parameter. And then when the function works, it goes, oh, I'm working on something that's at an address. I will put all my results at that address. And that is how it's being changed, because the variable itself in the other function has that address as well. And that is the magic behind reference parameters. Okay, does that sort of make sense? Sir? When the program ends, does it lose its name? Yes. Mm-hmm. Yeah. So, okay, so the question is, when the program ends, does the box lose its variable name? And the answer is yes. What's happening when your program is running, the operating system, like Mac OS or Windows or whatever you have underneath there, is handling all the memory for different programs that are running at the same time. And so when the program ends, the operating system goes, oh, that program's over, I can use that memory for other programs. So it does end things. Yes? Uh-huh. There's a special place of memory for that as well, and I will show you kind of how that works later in the semester. Okay? I mean, what we're talking about now is actually this memory management and where to put things in memory is actually something we cover in the operating systems class for senior level CS students. Okay? That doesn't mean that it's hard. I mean, I could easily explain it to you. It just, you don't really need to know it right now. Does that make sense? And when you're a senior, you actually look at how the memory is laid out, essentially so that if you're ever doing a program that you have to, if you have to manage where things go in memory yourself, you know the principles of it. And we're working on computers these days like that have Mac and Windows, but there's a lot of stuff that the operating system is non-existent or very primitive. Like if you're programming like a digital watch or some sort of embedded controller or something like that, there is no Windows to do it for you. You have to do it yourself. So you don't need to know it right now because the operating system takes care of it. But if you keep going, someday we'll teach you. So if you're programming on something that doesn't have an operating system, you'll know what to do. Yes? Okay, so the question is, in this program, can you access only things that have been used by the program, or can you access random addresses? The fact of the matter is you can access any random address you want. I just haven't shown you how to do that. We'll get to that shortly. Now, the other question we had was that we know that when the program ends, like the label that's on a box goes away, right? It's no longer X. When this program is done, whatever was at, 0x7FFFFBEC15D8 or whatever it was, that goes away. But does the value in there go away? And the answer is it does not. And the reason that weird things show up when we declare variables is because what you're actually getting is whatever variable was in that box last time it happened to have been used. And that's why. So the stuff that shows up when you don't initialize your floats or ints or something, is there because that was a piece of memory that was used in the past and it just happened to have something old in it. And it actually turns out that this is a security violation because what ends up happening is if you have programs running on the same computer, if one program is trying to figure out what's going on the other side of the program, it can just start grabbing random blocks of memory that aren't being used and look to see if anything was left over in there, like encryption keys or passwords. And it just turns out, this came out last night, so it's very relevant. There is a bug in OpenSSL, which is the standard encryption library that all sorts of websites use. You might have seen this in the news. What happens is, under certain circumstances, OpenSSL sends a message back that has a block of data, and the block of data is actually a block taken randomly out of memory that is sending back. So the bug is such that it's sending stuff over the network that is just random blocks of data from RAM, and you can search through this for things like encryption keys and passwords. So anyway, yes, sir. Yeah. No. No, the answer is no. The answer is, the question is vector. When you use vector, okay. So I've been lying to you all semester. I'm just going to come out and tell you right now. There's also a thing called arrays. Have you all run across arrays? If you declare an array is a static block of memory. It finds a space and puts it all together. The problem with an array is that you can't expand it if you need more space. And so vector is better. So when you get vector, it doesn't necessarily do this. I'm going to tell you one other thing. Project 5 isn't posted yet. It will be later today. Project 5 is going to be Project 4 all over again, except you will not be allowed to use any vectors. So you will essentially be duplicating the functionality of vectors, but you're going to be using this memory stuff that if we ever get to, instead of me going on about other things, you will essentially be replicating the functionality of the vector class through your own grabbing of memory and stuff like that. Okay, yes? Uh-huh. Uh-huh. Yeah. Yeah. All right, so the question is, can you just randomly go to a box and stick things in there? Yes, you can. Yes, and the question is, do you want to fill, if you want to fill everything in memory up with a certain value, can you? And the answer is yes. And do you know what will happen? Your program will crash. And the reason the program will crash is because part of the memory is holding your program, and you will overwrite your program with just some particular value, and the code that is supposed to be executing will then just be gone. Okay. Yes, so you can do all sorts of things with memory. So what we're getting at here is this ability to reach into a particular memory address and do things is incredibly powerful and incredibly dangerous, okay? So let me make an analogy over the course of the semester. When we started off at the beginning of the semester, we learned how to program with some stuff, and it was like I gave you a plastic child's axe and I told you to cut down the pretend tree and it fell over. Then we got to classes and I gave you a metal axe, except it was a little bit dull and you could do some stuff with a metal axe. What I'm giving you today is the snowmobile-powered chainsaw that people use in log cutting competitions to see who can cut the biggest log in the shortest amount of time. Okay? What we're going to get to, if I ever stop ranting about how good this stuff is and actually teach it to you, is it's called pointers, and pointers are incredibly powerful. Once you have a pointer into the system, you can do anything with it that you want. You can use it for good, you can use it for evil. Your computer, you're going to have a lot of crashes on the next project because you're going to screw things up at some point. And you're going to have a pointer that just goes someplace randomly in memory, and you're going to overwrite something that shouldn't be there, and your program's going to crash. Or your pointer is going to be pointing someplace in memory, you're going to say, hey, get something from there, and you're going to get some weird value back that doesn't make any sense, and your program's going to crash. Okay? A little bit this semester, more next semester, and certainly a lot in data structures, because data structures use pointers all the time. Okay. All right. Have you had enough of me prefacing, giving you the preview of coming attractions about how good this is? All right, let's take a 1-minute stand-up break. Don't go too far, and when we come back, we'll start looking at some stuff. Yes, the answer is yes, you could.
No, so when it comes to like overclocking the processor,
Uh-huh.
I'm assuming that uses like a random variable somewhere.
Overclocking?
Yeah.
Overclocking. So inside your processor, there's a clock that ticks at a certain rate. And overclocking it means you speed that clock up. And what happens is, depending on how the CPU is manufactured, it's rated for a certain speed. And what will happen is, as you turn that clock speed up, at some point, some of the components won't be able to keep up with that speed, and they will just generate errors. So.
What could you? So like I'm assuming the variable that tells it what speed to go at, or is it something that's more of a hardware thing that you would?
It depends on it.
Like a program?
It depends on the processor architecture. Some processors you can literally say speed up or slow down. Some have a max, and you can overwrite that. Like a processor that's in a cell phone that you want to be able to like save energy has essentially a setting that says go really slow now, because when it's not doing anything, you don't want it to use up energy. You can also turn that way up high and say, you know, sometimes it's set. It depends on the processor architecture.
But if you use like whatever pointer, you could like create a program that instead of
Okay, so now we get into the difference between so the operating system is doing things to protect other programs from your pointer. Okay, which is why your program's going to crash. What'll happen is eventually you'll say, I want to go over here, and the operating system will look and go, that's not your memory, you're done, and it'll shut you down. So, but yeah, pointers are awesome. I get very excited for you learning this. It's complicated and confusing and annoying, but. Mm-hmm. Java does not have pointers. Java only has reference variables. Java has pointers underneath the language because it's doing stuff with the reference variables. You cannot create your own pointer. Mm-mm. So. No. Mm-mm. There's ways of doing it, but you just do it with reference values instead of pointers. So, Java, I mean, I'll be honest, switching from C++ to Java would take you like a week. Like it took me a week. I'd never programmed with Java before until like 5 years ago. And I was like, I want to learn some Java. And so I sat down and wrote some stuff. So. All right, welcome back. So now that we've had our big preview of coming attractions and I've told you how awesome everything is going to be, let's actually get to the point where it may not be so awesome. So in our program here, right, we have int x equals 19. We output it. We show where x is. We show the address of x. And we've seen this ampersand operator before as a reference parameter. So what was really going on with the reference parameter is saying, hey, go to this address and work with the thing at this address, which is how changes are being affected, right? Because all the functions are working with the same memory address. Okay, so now that we have an address, what can we do with the address is the question, right? We can print it out, clearly, because we printed it out. Do you think we can store it somewhere? Yes. Yes, we can. So here's what we can do. We can say something like int x is an int. Okay. So, I'm not sure I want to do this one first. Let's think about this for a sec. Okay. So, let's do this first. Did I spell that right? Dereference operator. Okay, so we have star. Star is the dereference operator. And what star means is it means go to this address and use what is there. Okay? So star means go to this address and use what is there. So here's what we can do. We can do something like this. We can say dereference the address of x, which means go to the thing that says x's address, and when you get there, set it equal to 12. And we're never actually going to do this very much. I mean, sometimes we will. But we're going to, was it 19 before? Yeah. And now we can say cout angle angle x, angle angle end line. And what we can say is, here, get x's address, dereferences it, which means go there, and when you get there, make it equal to 12. So what is this x going to print out down here? 12. It should print out 12. God, I hope it prints out 12. So we run it. So here's what our program did. We set x equal to 19. We printed it out. It was 19. We said, hey, where is the address of x? And it was at 7FFF50B, blah, blah, blah. And we said, go to the address where x is. And when you get there, set it equal to 12. So if ampersand is the address operator, and we're working on something that's an address, the star is the dereference operator, which means go to that address, and when you get there, do something with it. Everybody with me on this? So let's think about this for a second. How many of y'all have ever had to deliver pizzas for a living? Anybody? Me either. But let's think about this for a second. Let's say we were in here and I had a pizza for you and I told you, hey, take this pizza to Clay. Where would you take it? To me, because you know my name, right? What if I told you, hey, take this pizza to somebody name a dorm on campus? Any dorm. Harbin? Take this to 201 Harbin. Would you be able to go to 201 Harbin? Who lives there? You live there? In 201? No way. All right. I didn't mean to pick you out. I had no idea that you live there. In fact, I don't even really know where Harbin is. That's how sad it is. All right. How about 301 Harbin? Would you prefer that? You what? Aw, you're messing with me. Okay. Well, you know who lives there. So no, actually, this works out well. You know who lives there. You don't have. Let's just call them John. Let's say John lives there. Is that who lives there? Because not. Okay, Joanne. Thank you. So if I told you to take a pizza to Joanne, you'd go, oh, I know where she lives. She lives in 201 Harbin, and you'd go there, right? If I told you to take this pizza to 201 Harbin, you would go there, right? Either one works. Everybody with me on that? Either one works. And the analogy is, if we have the name of the variable, we can work with it. Just like if we have someone's name, we can take a pizza to them, right? If we have someone's address, we can take something to them. Just like if we have the address of a variable, we can work with it. And the way that we work with something that we have the address of is by using the star. The star means you have something that's an address, go there and work with it, and it is the dereference operator. There are two ways we can work with things. One is by name, and one is by address. Everybody got that? How can we work with a variable? First by, and then by. Which way have you been using all semester? You've been using name, but surprisingly, you've also been using address a little bit. You just didn't know it. When you use a vector with the square brackets, there's some address magic going on behind there. So when you say like square bracket 3, it looks up and it goes, oh, that one is the third one, I can go there. Okay? So you have been using addresses, you just don't know it. Now we're making it explicit. So when we say star parentheses ampersand x equals 12, we're saying find the address. Then we're saying go to this address, and when you get there, everything's equal to 12. Everybody good so far? Now, let me ask you a question. Let me say, I don't know, somebody give me another dorm, so I don't know any of them. I know Darnell. Okay, so let's say you're going to like 508 Darnell, right? Who lives there? Anybody know who lives in that room? I don't know. Could you go there? Okay, so as we've been working throughout the semester, every variable we worked with has a name, but now we also have this address, and it turns out that we can have variables that do not have names. And that's where we're working towards. Eventually, we're going to have variables that do not have names. What do they have, though? Addresses. So if we have a variable that has an address but no name, can we still work with it? Yes? How many of y'all think we can? All right. So, and how do we work with that variable? If I give you an address but not a name, how would you go to that variable? With the star operator, the dereference operator. All right? Everybody with me? Everybody understand the difference between a name and address? Everybody happy that you can work with a variable that you have the name of? let's look at how we work with the variable that we have the address of. So here we have worked with something with the address. Now I want to show you something. It turns out that we can store the address of a variable. And we can hold that in another variable. And this is what we're going to do. We're going to say int star y equals ampersand x. Okay. One of the confusing things about working with memory addresses is that the star operator is used in different contexts. It's the same operator, but it's used in different contexts, and it can get confusing. Okay? In this context, where it precedes the address of a variable, it is the dereference operator. In the context where it antecedes, what's the opposite of precedes? Where it comes after? Where it comes after? Where it comes after, it means that the variable holds an address. All right? The designers of the C language wanted this, they had this logical way of why they did this. And I cannot quote it because it doesn't always make sense to me. So we just have to go bulk memorization. When the operator is before a variable that holds an address, it is the dereference operator. When the star symbol is after a variable type, but before a variable name, it means that the variable holds an address, and we have a particular name for this, and it's called a pointer. Okay? So what we have here is int star y means that this thing is a pointer. It's a pointer to a variable that holds an integer, and this variable name is y. So this declaration, int star y, means y is holding address. It's holding the address of something that stores an integer. Okay? And y is called a pointer. So y is a pointer to an integer, and a pointer is an address. Everybody with me so far? How many of y'all are with me? All right. So now we're storing there. So now we can manipulate y just like we could x. So we can say cout angle angle y, angle angle ENDL. And what is this going to print out? What's this going to print out? It's going to print out the address. And let's see if that's the case or not, okay? Let's see if that's the case or not. So I'll compile the program. I will run the program. And you can see that x's value is 19. It was stored at 7FFB8, F7, blah, blah, blah. We changed it to 12, but y now still holds that address, okay? In fact, you know what I should say? I should put y is, so we can see what y's value is. And now we can see, when we run, that y is holding the address of x. Everybody good on that? Make that a little bigger. Whoa. Sorry. I tried to make the font bigger. There we go. All right. Questions, sir? Okay, a pointer is something that holds an address, and the way we would say this is y is a pointer to x. Because when you say a pointer is like the address of, which means if you follow it, you end up there. I explained that very poorly. But it's a pointer if it holds the address of something else, and we could say y is a pointer to x, because y points us to x. Okay? So let me use an analogy here. The dereference operator is, you're delivering a pizza, go ask the person in 508 Darnell where this pizza goes. Okay? Or go ask Joanna in 201 Harbin where this pizza goes. And so you go get the address, and then by dereferencing the address, it tells you where to take things. And I've just completely muddled the analogy up, didn't I? Because I'm judging by the number of lowered eyebrows. Yes? Yes. Y is a completely different box, and I didn't draw the picture, but there is a box named Y. It's at a different place than X, And inside that box, instead of holding 12 or 19, it holds 0x7ff, whatever that is. Y is a pointer to x, so if you were dereference y, you would end up at x. Okay? You would end up, you would end up with the value that was at x. Okay, so let's dereference y. So, what is the dereference operator? All right, so y holds the address of x. It's a pointer to an integer because x is an integer, right? When you declare a pointer, nope, not down here, because this is the dereference operator. Dereference operator, we know that y holds an address. How do we know that y holds an address? Because there is a star in front of it in its declaration. So when you see int star y, that means it is not an integer. It is the address of something that is holding an integer. It is a pointer to an integer. Everybody with me so far? Sir?
So is an address like a type?
An address is like a new type. Yes, it is a big number that represents someplace in memory. So this addition of a star is like we've added a new type. Okay? And the type is a pointer to a particular type. The address of a particular type. Everybody with me? Yes? All right. So when we dereference y, what is this going to print out? How many of y'all think it's going to print out 0x7ff something? Anybody? How many of y'all think it's going to print out 12? How many of you have no idea what it's going to print out? How many of you wish you were someplace else today? No one? Just not admitting it. Nothing wrong with that. I sometimes wish that myself. Okay. So let's see what happens here when we compile and run this. We'll compile it. We'll run it. And you can see what's going on. X is 19. It is stored at 077. We change it to 12 by dereferencing the address. We set y equal to exactly the same address, and when we dereference y, it goes to the same box in memory. Okay. Would it help if I drew a picture of this? Great. Yep. Go to that address. It says go to that address and then use it. Okay. So here's what we've done. Here's our RAM, and we have a bunch of boxes. And at first we declared a box named X, and we put 19 in it. And this box had an address, which was something like 0x7ff3 ... Right? Actually, just for purposes, I'm just going to call this address 07ff3. Okay? We all know there's a lot more digits to that, but are you good with this? Everybody understands this part. We declared an int named X, we put 19 in it, and it happened to be stored at that. We manipulated this by address. We dereferenced this address, and then we changed it to 12, and that was fine. And then we declared a variable named y. What type is y? It's a pointer to an integer. It has the star in its name, so it's a pointer. And what value is stored in here? Y stores the address of x. And if we do things with y, if we dereference y, that star operator, if we say star y, it says, oh, star y. Well, y is an address. We're using the star operator, which means I actually go to, so this right here, star y means go to that address, and when you get there, do stuff at that address. Yes? Okay, so here's the deal. We are never going to use the ampersand operator again. Okay? We will use it for value parameters, but we are not going to be using it to get addresses of things. The only reason I show you the ampersand operator is because I'm trying to get into your minds that there is a link between the name of a variable and its an address. Okay? What's going to happen is as we go along, we are going to see how to work with variables that have no names. They will not have a name. And if they don't have a name, we can't use the ampersand operator with their name to get the address because they just don't have one. All right? But in order to show you how these pointers work, I'm trying to show you that things have a name and address. Yes, ma'am? Yes. If x was a string instead of an integer, it would say string star y. So this type right here, the int, matches whatever you're pointing to. Okay? And then the star always means it's actually a memory address that's stored in there. Sure. So the question is, can you have a pointer to pointer? And the answer is yes. It's called a double pointer. You can have triple pointers. You can have quadruple pointers. You can do that as many times as you like. For your sanity and mine, we will not do that in this class. Okay? They are very useful for some things. And in fact, they're used all the time. All the time. So anybody ever heard of this program? I don't know if you've ever used it. It's called Excel. Anybody heard of Excel? So in Excel, every one of those little cells, when you say, like if you put equal A3 in there, like you're relating it to another cell, it's actually creating another pointer to that other cell. And Excel, when you program Excel, it is nothing but a giant mess of pointers everywhere. Pointers to pointers to pointers to pointers. Because you could see, like if you had one cell, if you said set the cell equal to A3, and A3 says it's this 2 times B2, and B2 says it's 9 times G7, it follows all those things around to do the computation. So you can have double pointers. Yeah, but like I said, for your sanity and mine, like if I tried to teach you double pointers, like nobody would ever take 052, right? That's something we inflict upon you later when your sanity is up to it. Actually, they're not that bad. I mean, it just, yeah, if you have a pointer to a pointer, it's just star star y. So that's all. Or you have as many of those as you need. But yeah, it's rare to see more than 2 stars. I've seen 3 stars, I think, on one occasion in real code. But the problem with it is that it gets really hard to reason about, like, because you're got links to links to links, which gets confusing to think about. So. All right, how's everyone doing? Everybody doing good? Think so? All right. So, the weird thing about what we've been doing so far, is that we have this variable named x that that we're using, and it has its own address and it has its own name, but we're using it that way anyway, which is weird, isn't it? So I'll tell you what. Let's create a variable that has no name, the mystery variable, the spy secret stealth variable. Are you all good with that? Yes? Here's what we're going to do. And this is going to be quite shocking. Actually, I should have buzz fed that. We're going to do something so shocking now you won't believe what's going to happen next. Okay, here's what we're going to do. We say y equals new int 23. You haven't seen this before, but this new is a special keyword. And new tells the compiler, hey, go out and find space in memory where I can store an int and tell me what address it is. Okay? So what new does new finds a space in memory that can hold the right type and returns the address. So when we say y equals new int 23, here's what we can do with this. We can do a couple of things. We can see what space was available. And how do we see the address that y holds? Yep, if we see out y, we get the address. If we want to see what was in that space, how do we see out what's in that space, actually? We have to dereference it. Y'all are getting this. Okay, so we're going to see what space is available, and we'll definitely be able to see what is in that space. Yes, sir? All right. All right. Yes? Yes. Any sentence in this class that starts with can you or could you, the answer is yes. It's just a matter of how. Do you want to finish your question? I'd rather, let's go through this first. And then we'll, okay? So here's what we've done. Y, what did Y used to have in it? The address of, it was a pointer to. Now what we're doing is it's saying instead of having the address of X, have the address of this new integer and hold on to that for me. So Y is going to change value. The assignment operator works just as it always has. That means we're changing the value of Y to something else. And then we're printing out what Y is. This is going to be an address. So it should be 0x something. Anybody want to guess what 0x it's going to be? Okay, we're guessing 70. I'm guessing it's going to be in the ones. It's going to start with a 1, 0x1 something. Okay? And then we'll print out, dereference it and see what's there. It's totally unfair. I've been doing this forever, right? We're dereferencing it, and when we dereference it, we find it has what value in it? It should have 23, because we're saying create a new int and make it 23. So let's see what happens when we compile this. We compile it. It compiles successfully. We run it. Oh, it did do 7. Wow, I'm surprised by that. Okay. So here's what happened. Initially, Y, let me put some printouts in here so we can see. Okay, so we create a new integer. We use this new keyword. What does new return? What value does new return to you? It returns an address. Every time you use new, it returns an address. Okay, it doesn't return a value, it returns the address. And when you do new something like this, int 23, it puts 23, it says at that address there's an integer with the value 23. We're now changing Y to point at that address, and then we're saying the thing that Y points to holds star Y. So let's run this. And we run it, we can see we have a named variable named X. It has a value named 19. X is stored at the address 07FFF. When we change it using the dereference thing, we change it to 12. We say Y is initially pointing to X. It has the same address. Then we use the new command, and Y changes to point at this other thing, 0x7f8, and the thing that Y points to holds the number 23. Let me ask you a question. What is the name of the variable that is storing the number 23? What is the name of the variable? I got a candy bar. Your choice if you tell me the name of the variable that holds the number 23. Yes? What's the name of that variable that holds the number 23 in it? Yes? There isn't one. That was a trick question. I'll give you candy anyway, so you don't want to. Okay. There isn't one, okay? That was a trick. We are now at the point where we can have variables that do not have names. They do not have names, and we can work with them. And I know where this question is going. Yes? What's the point of having a variable that has no name? Right? Everybody with me? But everybody's good. Everybody understands this. We have variables with names. They may have a name and address. We have variables that only have an address, and we can get there by dereferencing. Everybody good with that? All right, stand up for 1 second and take a break. 1 minute break in place. Yeah. I'll put it up on Blackboard today too, so you can play with it. y changes to because we're right here. Y equals or changing y because we're setting it equal to something different, right? When you use the equals, that's the assignment. And what it's changing to is the result of this. The result of this operation. And new says, go find a place in memory for me that can hold an int. And while you're there, put 23 in it. But tell me the address of where you put that. Okay, so new says find space for this, put this in there, and tell me where you put it. The address of where you put it. Yep. Does that make sense? And so what's happening is now y is pointing at some box that holds 23. But we know it doesn't have a name. There is no name. You can't say x equals or y equals. You cannot because it only has an address. You have to dereference it to do anything with it. Yeah. Mm-hmm. All right. So let me update our diagram for a second. Okay? Let me update our diagram. So here before we had x was changed to 12, y was pointing at x. What happens now in this diagram, and I should have made some slides for this, but I don't like switching between slides and code. What happens now is we're changing the value of y. And y gets changed from whatever the address of x is to, what was it, 7, 8 something? Right? 7F8. Wait, what's going on now? All right, 7FB, right? 7FB. And what happens is someplace down here in the system, there's a box at that address that has that number in it. What is the name of this box? Doesn't have one. How can we ever get to this box? By looking at the address that y holds. So we know the address is in y. We say, hey, y holds the address. We dereference y. And when we use this dereference y operator, it ends up taking us to the box that has 23. Now, yes, sir? Okay, so we'll talk about that. Okay, so the question was though is how does this help us? Right? Does this help us? Because before we had the name of something and we could access it by name. Now we have this named thing y, and we have to use the name of y to get to this other number 23. Right? So did that help us at all? Not really. It didn't really help us because before we had one thing with a name we could access. Now we have one thing with a name that we have to use to access this other thing. And that sucks. Doesn't that suck? So, you know what? I'm going to put the screen up for a second. It's the first time I've done this all semester. Let's see if it works without turning off the projector already. Oh, sweet. Okay, here is where we are going with this. Here's where we're going with this. Let me just ask you a question. Let me think about how to phrase this for a sec. What does an int hold inside of it? An integer. It holds one value. Do we know anything that can hold more than one value? A vector can, but a vector holds all the same type of value, right? Do we know anything that can hold different types of values? An object or a class. So how about this? Let's say we have some sort of class, and the class inside has as one of its members, data members, the address of something else. I'll just show you where we're going with this. At some point we're going to have, I'm going to draw pointers like this. I'm just going to call this node for right now. Node is the name of the class. What this has is that we have a variable named y. It is a pointer, which means the address of a node object. You with me? All right, and what this means, and I'm going to draw a diagram of, is that this points at a node object. Pardon? Ah, okay. Oh, you're right. Look at that. All right, we'll see if that turns on again someday. All right. Is that better? So this is the address of a node, and the node lives someplace off in memory. And the node is going to have two parts to it. Two parts to it. The first part is going to be some data. Now, do we care what type of data it has in this case? No, we don't. It could be an integer. This data could be an entire class. It could have vectors. It could be a whole bunch of stuff. Whatever type of data we've talked about the entire semester can be in there. Okay? Because it's a class, right? And can classes have variable things inside? Say yes. All right. So we have some data, and we don't really care what the data is. The thing that we care about is that in this node, we also have a node star next. What that means is that inside this node, there is the address of another node. Now, what does that give us? This essentially gives us a pointer to some other node. What does this node have inside of it? Some data and what? Some data and you can see each one of these classes has the address of the next thing in line. This is a node class. It's got some data. Sir. Nope, each box is holding one address. Nope, each box has a bunch of stuff. This box is a collection of things. One of the things in this box is some data. We don't really care what type of data for right now. It could just be a single integer. It could be, oh, I don't know, a first name, last name, age, gender, and camp. If that is the type of data you would like to have in there, right? But the important thing for us conceptually right now is not the data. It's the fact that it has a pointer to another node. Now, which one of these objects out of all the ones I've drawn on the board has a name? The first one has a name. What's its name? What's the name of this one? Nope, that's not its name. That's how you get there. There's no name. How about for this one? There's no name. How about this one? There is no name. How do we get to that last node then? What we have to do is we say, well, we have y. Y has a name. So let's dereference y. Where does that take us? To the first node. Now, we have this address. Let's dereference this next member here. Where does that take us? Let's dereference this next member here. Where does that take us? So, before, in our example before, y was pointing essentially a pointer to one thing, an integer. But where we're going with this is that instead of y pointing at one thing, it points at something that itself has other addresses inside. All right? It points at something else. These objects out along here do not have names, but they do have addresses. And so we can still find them. Okay. What this is called right here is a linked list. A linked list. The next project, we're going to be working with linked lists. The goal of us working with linked lists is in part so you understand linked list, but it's mostly so that you get practice using pointers. Mostly so you get practice using pointers. Now, at the beginning of class, I was talking about other classes that you're going to take as you go along. Eventually, you're going to reach a class called data structures. The idea behind data structures is teaching you how to organize memory when you're writing a program in a way that solves your problem fast and efficiently. So let me give you an example. Let's say that we were the NSA. Have I used this example with you all? I think I did, like on the first day or so. But I'll just show you where we're going with this. Let's say we're the NSA, and we want to keep records on every single person in the United States. How many people are there? 300 million plus. We put that in a vector. How big is that vector? Big. It's a big vector. How do we search on a vector? So we want to look in this vector of 330 million and find one particular person. How do we do that? For int I equals 0, I less than or equal to 330 million, I plus plus. If person square bracket I equals suspect, we're there. So we start grinding through this big vector. How fast is that? Not that fast, right? Not that fast. Let me show you something that's faster. So what we're going to do is we're going to build a data structure, and it's one of my favorites. It's a data structure called a trie. Here's what happens. We have a pointer at the top, except it's not one pointer. It's 26 pointers bundled together, okay? The first one's for the letter A, B, C, D, all the way across. What's the next thing down here? A bundle of 26 pointers. Right? What's at this level? 26 pointers. So CL, the next one will follow A. If we're just going to do my name, Y. So we have this structure now. How do we find Clay? How do we find Clay out of this data structure? Well, C is 4, so we go to the fourth pointer and follow. Oh, C is 3, geez. C is 3, actually 2 by computer science counting, so we go here and follow that one. Next letter is A, we follow L. I'm getting tired. It's been a long day. And it's not even, it's barely afternoon. We follow L, we follow A, we follow Y. How many things have we had to look at to find me? 4. How many did we have to look at in the vector of 330 million? On average, if you do this over and over again, you expect to find it about halfway through. So you had to look at 165 million. How much faster is this? This is rockin' fast. This is amazing. And you know what? You use less memory too, because if you have a vector, you have everybody's names stored over and over again. Here, any names that overlap, you only store once. Okay? So, this is why we use pointers, because pointers allow us to come up with incredible data structures like this that will let us solve our problems quickly and easily and efficiently. All right? So this is where we're headed. Today, what I have shown you is I've shown you that variables don't have to have names. They can have addresses. You can have variables or objects that never have a name. And instead, what they are is the object itself has a pointer to the next object. At least 1, sometimes 2, sometimes 26. All right? And you build amazing, cool things out of these. So, Project 5 will be posted later today. You are essentially going to be doing Project 4 over again, except with a linked list instead of a vector. And it gives you practice with pointers, and the whole point of pointers is that when you go on, you can do amazing, cool things. Have a good Wednesday.